This resource is the first in a three-part series on polar coordinates. Part 1 defines polar coordinates. We consider how to convert from rectangular to polar coordinates and look at examples. We also discover how to convert from polar to rectangular coordinates and look at examples. Part 2 considers complex numbers. We consider the complex plane and how to graph complex numbers. We consider the polar form of complex numbers. We discover how to convert back and forth between the rectangular and polar form for complex numbers, and look at multiple examples. Part 3 looks at De Moivre's theorems, which provides a method for raising a complex number to a power. The theorem is formally defined. We then solve examples, both for complex numbers given in rectangular or polar form. Suppose someone asked you for the shortest directions to walk someplace. Most likely, you would give a direction and a distance to travel. For example, walk 5 miles to the northeast. You would probably not say to go 3 miles east, then 4 miles north. But that is exactly how we plot points. We give a left-right measurement and then give an up-down measurement when we look at traditional Cartesian coordinates, which are the xy coordinates we are most familiar with. However, there is another form of coordinates called polar coordinates. These coordinates are more in line with how we would actually give directions. They look like r and the Greek letter theta. R is the distance from the origin. Theta is the angle that the straight line path makes with the positive x-axis. But how can we actually find these coordinates? Look at the right triangle pictured that is formed with legs of length x and y and the hypotenuse of length r. We also see the angle theta that is formed from the positive x-axis and the hypotenuse. If we know the values for x and y, then finding r is simply using the Pythagorean theorem. A squared plus b squared equals c squared. Using some right triangle trigonometry, we can also set up the tangent ratio for angle theta. Tangent of theta equals y over x. To find theta, we would take the inverse tangent of both sides of the equation. So theta equals the inverse tangent of the ratio y over x. This works so long as the x value is positive. Anytime the x value is negative, this means we are in quadrants 2 or 3. The default for scientific and graphing calculators is to give the quadrant 1 or 4 values for the angle. To adjust, we just add 180 degrees to the inverse tangent. Let's look at an example. First, we want to find r, the distance from the origin. We have the solved out version of the Pythagorean theorem. R equals the square root of the quantity x squared plus y squared. We plug in our values. After solving, we find that the distance equals 5. Now we want to find our angle theta. Our formula is theta equals the inverse tangent of the ratio y over x. We plug in our values. This tells us that our theta is 53.1 degrees. So the Cartesian point 3, 4 is equivalent to the polar coordinate 5, 53.1 degrees. Let's look at one more example. What if we have the point -5, 12? Again, we have the formula to find r. We plug in our values. Solving, we find that r is 13. Now let's find our angle measure. We need to recognize that the x value from our point is negative. This means that we will use the alternate formula to find the angle. So theta equals 180 degrees plus the inverse tangent of y over x. Plug in our values. Solving, we find that theta is 112.6 degrees. So the Cartesian point -5, 12 is equivalent to the polar coordinate 13, 112.6 degrees. But what if we know the polar coordinates and we want to find the Cartesian coordinates? Again, we look at the right triangle pictured that is formed with legs of length x and y and the hypotenuse of length r and angle theta. We have values for r and for theta. Using this known information, we can set up appropriate trigonometric ratios. We have cosine of theta equal to the ratio of x to r. Multiplying both sides of the equation by r, we find that x equals r times the cosine of theta. We have sine of theta equal to the ratio of y to r. Multiplying both sides of the equation by r, we find that y equals r times the sine of theta. So this means that the polar coordinates r, theta is equivalent to the Cartesian point r cosine theta, r sine theta. Let's look at an example. Suppose we want to find the Cartesian equivalent of the polar point 3, 30 degrees. We have our formula to find the x value. Plug in our values. So our x coordinate is 2.6. We also have our formula to find the y value. Plug in our values. So our y value is 1.5. So the polar point 3, 30 degrees is equivalent to the Cartesian point 2.6, 1.5.